All right, so why? Why does doubling the concentration double the rate of reaction? Why does sometimes doubling the concentration quadruple the rate of reaction? This is our theory as to why. This is the model of kinetics. It's called the collision theory. So the idea is in order for a chemical reaction to take place, the molecules or the atoms or the ions have to slam into each other. So dependence on number of collisions, the dependence of the number of collisions on concentration. So if the red ball or reactant blue has to be smacked by reactant red in order to react, if I double the concentration of the blue one, I double the opportunity for collision. If I double the concentration of the red one, I double the opportunity for collision. So if I double both of them, I get 1, 2, 3, 4 times the opportunity for collision. So this explains second order. Doubling the concentration of both reactants quadruples the rate of reaction. So it's strictly about opportunity for collision. So I have 4 blue ones and 2 red ones. If I have, what do I have? I have 1, 2, 3, 4, 5, 6, 7, 8 opportunities for collision. If I double the concentration of the red ones, I now have 16 opportunities for collision. So I double the rate of reaction. So higher the concentration of the reactants, higher the number of collisions, the faster the rate of reaction. So it's that easy. In order to react, the two reactants must encounter one another, so i.e. collide. So if I'm going to break a bond, right, if I'm going to break the green one off and form a new bond between the big red ball and the blue ball, there's going to be a point where I've got to dislodge the green one and establish the blue one. So there's a point where the green one hasn't left yet and the blue one hasn't attached yet. So this is what's called an activated complex. A point where I haven't quite broken the bonds I have to break in order for the reaction to occur, and I haven't made the bonds I have to make in order for the reaction to occur. So short-lived transient species means that when I stick my hand into the pot as this reaction is going on, I can't collect this. It's not a reactant, it's not a product. It's neither. It hasn't happened. You haven't quite gotten the reactants to turn to products. You haven't quite gotten the products from the reactants. All right, so if you went statistically just on opportunity for collision between the blue ball and the red ball in terms of a reaction occurring, when I actually look at how fast the reaction is going, it's going a lot slower than the opportunity for collisions. So there's something else that goes into rate of reaction. The answer to this was proposed by savant Arrhenius. In order to react, colliding molecules must possess enough kinetic energy to overcome repulsive bonding forces of the reactants. So say, hey, let's just take a hydrogen bonding with a hydrogen. I mean, what surrounds a hydrogen atom? Electrons. So if you're coming in super, super soft, you got electron-electron repulsion, they won't react because you won't get through that repulsive situation where before the protons start to take over and attract the electrons. So it's about coming in with enough energy. So not only do you have to hit, but you have to hit with enough energy. All right, so this is called activation energy, the minimum energy required for an effective collision. So at a certain temperature, only a certain fraction of molecules possess enough kinetic energy for an effective collision. So we're back to our Boltzmann distribution. All right, so the line represents if you're beyond the line, right, in terms of speed, you have enough kinetic energy to react. So if you're before the line, you're not going to react. If you're past the line, yeah, you'll react. So if I increase the temperature again, what I'm doing is increasing the number of collisions, and not only that, they're hitting harder. So they're hitting harder and with enough activation energy to react. So you shift the distribution so that more particles now have enough kinetic energy to get an effective collision. So this is why reaction rate is temperature dependent. Not only to hit more often, but you have to hit hard enough. So if I'm looking at a rate law, right, rate is equal to K times the concentration of A. It's not about the concentration in terms of what's affecting the rate in terms of temperature. It's the rate constant. So there's a direct relationship between the temperature, increasing the temperature, and getting a larger magnitude on the rate constant. So bigger temperature, bigger rate constant. So rate constant is temperature dependent. An increase in temperature increases the rate of almost all reactions. I don't know, for our purposes, all reactions. All right. Faster moving particles collide more often and with greater kinetic energy. So you get a twofold effect. More collisions and more effective collisions. So way back when we were doing thermochemistry, it was all about the difference between the potential energy of the reactants and the products, right, in terms of how much heat was going to be released or how much energy is going to be released. Well, now we're concerned with that hump we ignored before. That hump represents the energy barrier I have to get over in order to get an effective collision. So in order to get an effective collision, right, dislodge C and replace it with A, right, come with enough energy to get through those repulsive forces, I've got to hit the top of the hump, right? So this distance from the potential energy of the reactants to the top of the hump represents the activation energy. Right? Exothermic reaction, right, was releasing heat energy. Endothermic reaction is the amount of heat absorbed. As far as the hump goes, it's the same thing. It's the distance from the potential energy of the reactants to the top of the hump. All right, so not only do you have to hit hard enough, but you also have to hit in the right orientation. I mean, if I'm going to get a activated complex between the blue ball and the red ball, the blue ball has to hit the red ball. So if it comes in and slams into the green ball, I'm not going to get a reaction. So anytime you make a situation where a collision has to occur with a particular orientation, you're slowing the reaction up. So a lot of reactions go really slowly because you have to hit in just the right way in order for the reaction to occur. A lot of times enzymes speed up reactions because they hold molecules in a particular orientation. So you get more effective collisions with that for that reaction. All right, so rate of reaction is directly proportional to the number of collisions per second with the proper orientation, the fraction of the collisions that possess a sufficient energy for the reaction to take place, i.e. the activation energy. So the rate constant, right, the magnitude of the rate constant, big rate constant, fast rate, is going to be proportional to some frequency of collision term, right? Different reactions are going to have a different A value, right, depending on what the orientation issue is for collision. Multiplied by E raised to the negative activation energy divided by RT. So with this expression, right, the Arrhenius expression, we're equating K to the frequency of collision, activation energy, and temperature. So know two of the terms, you can figure out the missing one. R in this case, since activation energy is usually in kilojoules, we want to put R in kilojoules. So instead of 8.314 joule mole K, we use 0.008314 kilojoule mole K and use that value for R. Right, R is the gas constant, right? 0.0821 liter atmosphere mole K or 8.314 joule mole K. So we just have to move the decimal point and use kilojoules if we're going to use this equation. I can rearrange this equation. So if I take the natural log of both sides to get rid of the base E and rearrange terms, I can come out with an equation for a straight line where if I plot the natural log of the rate constant versus the inverse of the temperature that the rate constant's at, I can get the slope of the line. The slope of the line is equal to activation energy divided by R. So you're going to get a negative slope. So if I have rate constants at different temperatures, if I take the natural log of those rate constants, plot them versus the inverse of those temperatures, Of course, we can't have it in degrees Celsius. Just quickly flicking back to the Arrhenius equation. T is the absolute temperature, right? So it's got to be in Kelvin if we're using R. So get it in Kelvin. Take the inverse. Take the natural log of K and then plot. I end up with a straight line with a negative slope. The slope of that line is equal to negative activation energy divided by R. So I know what R is. R is a constant. So if I know what the slope of the line is, I can rearrange and solve for what the activation energy is. Make sure everything's in the right unit, and I can get the activation energy. An alternative form of the Arrhenius equation, I'll give you both on the test. You can derive or switch it around algebraically, so you come out with this: the natural log of one rate constant compared to another is compared to the inverses of the temperatures that they're taken at. And in this way, we can figure out what the K value will be at one temperature versus another if I know what the activation energy is. So you can plug it in this equation and find the missing variable. Find the activation energy, find the temperature at K1 or K2. So for a first order rate constant, we have a K value of 3.32 times 10 to the minus 10 per seconds at 25 degrees Celsius. Calculate the rate constant at a higher temperature. Right? So if we know what the rate constant is at one temperature and we know what the activation energy is, I can plug in and find out what the rate constant is at the new temperature. So plug into this permutation of Arrhenius equation. Solve for the rate constant at the new temperature. So what did we do? We raised the temperature. Rate constant should have gotten bigger. It did get bigger.